So what have we been doing? We learned factoring first, right? And then we did long division and synthetic division yesterday, which you'll see later helps us factor more. I'm going to show you one of the benefits of factoring today when it comes to using when you're working with polynomials, and that's to be able to solve an equation basically, or in this case we're going to say find the zeros. So let's talk about some stuff here. I believe I printed a lot of this stuff for you guys already. So the roots of a polynomial are also known as the zeros or the x-intercepts. And once again, it's where it touches the x-axis. So on this picture here, the 3 yellow circles are the roots. So this polynomial would have some roots probably at about -0.6, 1, and maybe like 1.6. So it's like just estimating there. How do you find the roots of a polynomial? It's pretty tough a lot of the time. Sometimes you just can't, but in a lot of circumstances you can. And the main strategy we're going to use is factoring, and then we'll use zero product property. I can't recall if we've done that yet this year or not. I always get mixed up with you guys in Algebra 2, but I'm sure you'll recognize it when you see it regardless because you've done it in Algebra 2. Why do we care about the roots? Well, it's helpful for graphing for one, but also this process, like I said, it's just helpful for solving equations in general. Like I think maybe on your homework tonight, I'm not sure, maybe not. There's technically some questions where I could, you could solve a system of equations doing this. You could do all kinds of things. So the strategy is pretty useful for a lot of different circumstances. So let's jump in and we're going to do it. So go ahead and, did I print this one for you? So you'll need to write that down. So before we begin, like I said, I don't remember if we talked about this or not, so I want to make sure that we're all good. You don't need to write this, just watch for a second. If I told you we have x times y equals 0, what do we know about x and or y? One of them has to be 0, right? Because that's the only way you can get 0 by multiplication, if one of those things is 0. And that's unique to 0. It doesn't work for anything else. Like, for instance, if I said x times y equals 1, some students might be tempted to say, well, they're both 1. That's the only way that can happen. But that's not true. It could be like a half times 2, right? There's really an infinite number of solutions to that, so you can't do it. But with 0, it's special because there's only one way that can happen, and that's if one of those terms are 0. Okay? That's what we call the zero product property. All right, so we're going to use that fact to help us out here. So first of all, we want to find the roots. And you guys remember that means x-intercepts, right? And when you're on the x-intercept, that's when you're on the x-axis, right? And when you're on the x-axis, what's your y value? 0. So the first thing you're going to do is you're going to plug in 0 for y. That's how you find roots. That's how you find x-intercepts, is you plug in 0 for y. Okay? Now the next thing that we're going to do is we're going to factor this. So now we get to review. So what's the first thing you want to do when you factor? I think maybe you're saying what I'm looking for. It's not quite the word I'm looking for, though. There you go. It's called the greatest common factor. You always look to see if there's a GCF, right? And in this case, there is. I can divide both of the coefficients here by 2, right? And how many x's can I take out? So I can take an x out also. So if I divide 2x out of here and here, let's see what we'd have left. I'll put 2x underneath. First of all, 2 goes into 2 once, right? And then x goes into x to the 5th 4 times, right? So we got that. 2 goes into 162 81 times. And then x and x make just 1, but we'll just cancel them out there. Okay? So that's the first thing you do is you take out a GCF. Now this thing has 2 terms. What strategy do we learn for factoring polynomials with 2 terms? Difference of squares, right? So let's do that. So this is a difference of squares. So what we're going to do is we take the square root of this. What's that? Split it up evenly there. And then we're going to take the square root of that. And we make 1a and 1a. And then we keep checking to see if we can go further. So this is done. GCF, you never need to do anything with that. But this, the only thing that could be is a difference of squares. Is that a difference of squares? No, because it's plus, right? How about this one? Yeah, we could do it again, right? So let's keep going. So now you guys can kind of see why I was saying if you're a little rusty on factoring, today's going to be a little bit of a stretch for you. But don't worry, I'm going to let you guys practice factoring tomorrow. Good morning. Don't forget to grab a paper there. Good. All right, so that's the second thing you want to do. So first thing we do, since we're looking for roots, is plug 0 in for y. The second thing we do is we factor it completely. That means take it all the way down. That's supposed to say completely. I ran out of space. Sorry. All right. Okay. So we have 2x, x squared plus 9, x minus 3, and x plus 3 equals 0. Well, now we get to use the zero product property, right? I've got this times this times this times this equals 0. If those four things multiplied together equal 0, that means one or more, or possibly even all of those things have to equal what? 0. So now what we do is we do 2x equals 0, so that means 2x could equal 0, right? Or x squared plus 9 could equal 0, right? Or how about x minus 3? Or x plus 3. This is what we call the zero product property. The zero product property. So that's why we factored, because by factoring, we get a bunch of products, right? And that allows us to use this property. Now, these are certainly much easier to solve for x than what we started with. So in this case, just divide both sides by 2, and we get 0. So that's one of our roots. That's one of the places where this polynomial would touch the x-axis, is at x equals 0. Okay? Let's do the next one. Good morning. Nyla, there's a worksheet to grab over there on the table. Now for this one, we're going to take the square root on both sides, right? And don't forget, when you solve by taking a square root, you get a plus and a minus. And there's something else weird here, right? What's the other weird thing? Which means that's an I, right? And what's the square root of 9? These are imaginary roots, which means it actually doesn't touch the x-axis there. We could find them for today just for the heck of it, but we're not ultimately going to be doing anything with those really. Now, if I get some time, I want to do an extra credit lesson, a couple of them actually, and that will come more into play. But for today, you know, we probably won't be doing much with this, so I'm not even going to circle it, but it's nice to have on our notes. All right, over here. And here. So basically, this polynomial touches the x-axis at 3 spots: 0, 3, and -3. Okay?
So you only factor 9 because they'll get a real number?
Say that again?
They only did 9 because they could not equal 1. Because to do it in 3, get 1, 2.
I'm not sure I understand your question. Which one are you referring to?
X plus x squared.
This one?
Yeah.
And so what's your question about it again?
Why did you square it? I mean,
oh, because there's a 2 on there. So that's how you cancel out a square. You take the square root on both sides. Gotcha. Kondiker, can you turn it down for me? I can hear it all the way through, buddy. All right. Okay. So, that's that. So, three-step process. Ready? It's plug 0 in for y, right? Factor, zero product property. You got your roots. Okay. Something kind of interesting is let's see how many roots there are, and let's include the imaginary roots too. There's one here, right? There's actually two roots here because one's plus and one's minus, right? So that's 1 plus 2 is 3, 4 and 5, right? Now let's look at the original problem. Whatever that power is, that's technically how many roots you'll have, just so you know. Now, mind you, we really only have 3 real roots, okay? And also, you might sometimes have a repeated root. That means you might end up with 2 factors that are exactly the same, so you get the same root twice. So you would double count that one. In other words, that would count as 2 roots, even though it's really 1. But the point is whatever that number is there, that's how many roots you technically will get in this process. All right. So we're gonna let you guys try a couple of these. Let's do like one of them like a guided practice, and let's do the other one like a student practice. I don't know. What do we got to do yet? I think we do. Let's do one like that. No, I don't know. What do you guys think? You guys think you guys can handle this? How do you guys want me to guide you through one more? Okay, I'll do a guided practice and then we'll do the student practice. So let's call. In my opinion, number 2 is going to be harder. So I'll guide you through 2, and then I'm going to let you guys hit up 3. Okay. All right. So go ahead and write down number 2.
Why?
X.
Who's X-int?
Y.
Oh, This is funny.
All right, you guys ready? Here we go. So I'm gonna need some space here. It's Elijah. What is it? It's negative 6x cubed.
21x squared minus 15x equals.
Okay, so for the first thing, I'm just going to ask you what to do. So I'm going to ask Kalani, what do I need to do first? Okay, so we're all going to plug in 0 for y. Let's do that. Okay, so Andrew Arnold, what am I going to do next? Okay, let me try a couple more folks here. Elijah, what are we going to do next?
You gotta pick up the negative 6.
Okay, so you said a keyword there. The word is factor. We need to factor, right? And so now I'm going to ask to factor, what do we do first, Gabriel? To factor, what's the first thing we always check for? Okay. Want me to hand it off to Amanda? Okay. Amanda, what do you think? You always look for the GCF first. So that's where I'm going to pause, and I'm going to let you guys see if you can figure out what the GCF is. But you're going to have something here, and then you got to figure out these 3 blanks. And I want you guys to remember something we haven't seen in a little bit. Remember, what do you do when there's a negative in the front? You need to take a negative out as well. So when you take out your GCF, make sure you're taking out a negative version of that GCF. Okay? It wouldn't be wrong if you didn't. It's just that A, your work won't match mine if you don't. And then B, a lot of times it just makes things easier. So, there you go. 2. I like your X, but the 2 I don't agree with because 2 doesn't divide into 15 or 21. So, 3, I agree with that. And an X also, right? They all have an X. But when the front's negative, I said make sure you're taking out a negative. So now what you're going to do is you're going to figure out what goes on the inside. I'll pause again, give you guys a little more time. Inside here, Steve.
2x squared minus 7x plus 5.
Okay, so he is correct. Any questions? Okay, now the next thing we're going to do is we're going to, Amanda, we need to keep factoring this. So Amanda, what strategy do we use for that? Braden, what strategy do we use for that? The box method. Okay, so I'll give you a minute to see if you can do the box method. If not, I'll put the answer up in about 2 minutes or so. Why not, Maria? Gosh. It's okay. We'll practice it tomorrow. Let's see if maybe Nicole can help us out. Nicole, what did you get when you factored that? X what? Minus 1? Is that what you said? All right. Let's see if you're right. So we have 2x squared minus 7x plus 5. So what we should have done on this was we should have put the 2x squared here. Was it plus 5? Okay. So it's got to be 2x and x, right? It's got to be 5 and 1. The only thing is where they're located. We don't know. We might have to switch them. Let's see. If I fill in my box this way, I get 10x and 1x. Does that make 7? Okay. 10 and 1 can never make 7, so let's try again. I know it's got to be 5 and 1, but let's try switching where I put the numbers. So in this case, 2 and 1 makes 2, 5 and x makes 5x. Can that make 7?
Yeah.
Yes. Now what kind of 7 does it make? That would make a positive, right? But I want a negative. If it's negative, they both need to be negative. And if those are both going to be negative, then these should both be negative. 2x times x makes 2x squared. That makes negative 2x. That makes negative 5x. And that makes positive 5x. And this makes the negative 7 that we need. So we're good. Okay? And so, I lost my place. I would agree with what Nicole said. The only thing is I'm just going to change her plus 5 to a minus 5. Okay? Now I'm going to ask Madison, what's the next step after we've factored this? So plug in 0, factor completely, and by the way, we are done factoring because both of these only have 2 terms, and then neither one of them is a difference of squares, so we're done.
The 0 property.
Do the 0 product property. So I'll pause and I'll let you guys do that. We do the 0 product property, right? So that's where we take each piece and set them all equal to 0. What would this one give us?
0.
How about this one? Cool. Could write it either way. How about over here? So this polynomial touches the x-axis at 3 places, right? Okay, so that's your guided practice. I want you guys to try this one. See if you guys can work that one out. All right. So we have to change this to a negative, otherwise it wasn't going to factor right. So I apologize. Try again. Bonnie Ramirez, do you have a final answer for me? Okay. How about you walk me up to where you got, right? So you don't need to tell me this. I know we all plug this in for 0. Now, when you factored this, what did you get it factored to? Yeah? Okay, that's correct. Now, a few of you guys are using factoring by grouping instead of the box method. Some of us are making a little boo-boo there, I've noticed, but the box method people seem to be getting it. But that's what you should get. Does anybody need to see it? So the box method would look like this, right? So we have x cubed minus 3x squared, x and minus 3. So these two have in common a negative 3. These two have an x. These two have an x squared, and these two don't have anything, but we put a 1. So there's your x minus 3 and x squared plus 1. The factoring by grouping people, if you want to do it that way, I'm seeing quite a few people make a little bit error there, so I want to make sure if you want to use this strategy, you want to make sure you're doing it correctly. You group for these, right? You look for what they have in common. These two have an x squared in common, which leaves me with that. These two have nothing in common, but we do put a 1 there. And then we take out what this and this have in common, and that's the x minus 3. And then what's left, if we take that out, is the x squared plus 1. So whichever strategy you use, that's your result. So Xanim, what's one of my roots here? That's one of my roots. Very good. Yeah. So for this one, if you take the x squared plus 1, you make it equal 0. Minus 1, you get x squared equals negative 1. Take the square root. Don't forget your plus and minus, right? And then this is just I, right? Square root of, first of all, you take out your I, and the square root of 1 is just 1. So the answer is plus and minus I. So once again, it can't hurt to find those today. We're not going to be doing a whole lot with them, but there you go. All right, I want to move on to one more topic before we call it a day. This last topic is not as difficult to accomplish. It's still a little tedious, but it's not difficult to accomplish. Did I print? I think I printed this for you, right? See or no? No? Okay, then don't worry about it. You don't really need it. I just want you guys to watch something. Ready? Let's factor this by finding the root. Step 1, plug 0 in for y, right? Step 2, factor it. Step 3, 0 product. Step 4, solve. You guys good? So, now what I want to point out to you is, let's look at these roots. This root has a 5 in the top and a 3 in the bottom. Let's kind of work our way backwards and see where those net numbers came from. So this 5 came from here, didn't it? And this 3 came from here, which came from here, right? Now where did the 3, well, let me use different colors. I'm going to do the ones that are on the top in green. So 5's on the top, 5's here, 5's here, right? And I'll do the ones that are on the bottom in purple. Good? Let's do the same thing over here. On the top, here's 1, 1, 1, right? 2, 2, 2. Now look at these two green numbers here, 5 and 1. Where did they come from? They come from this number here, don't they? And where does the 3 and 2 come from? They come from that 6. So here's our conclusion then. No matter what polynomial you may have, we know something about it. If there are any roots that are actually, not weird, funky, decimal or imaginary things, here's what we know. What are two things that multiply together to make 5? What are two things that multiply together to make 6? 2 and 3, or I can make all kinds of fractions out of this. Couldn't it be 5 over 1? Couldn't it be 5 over 2? 5 over 3? 5 over 6? Or how about 1 over 1? 1 over 2? 1 over 3? Or 1 over 6? Here's what I know then. I know that my roots have to be one of these 8 numbers. Does that make sense? Also, the signs get a little bit tricky because it could be positive or negative. Okay, so here's what we have now. For this, it's too much work to do that. But I use this because it makes sense. With really big polynomials where factoring is kind of a nightmare, this is very helpful because then you know what some possible answers might be. Okay, so this is what we call the rational root theorem. So if there are any rational roots, that means fractions like a over b, or maybe just like 5, which is technically a fraction too, like 5 over 1. If there are any rational roots, meaning not square roots or imaginaries or weird things like that, then they will be the following things. It will be plus and minus factors of the last term over plus and minus factors of the first term. However, it's important to understand these are only a list of possible roots. They are not the actual roots. But there's a way you can tell. What's a root again? It's when y equals 0, right? So it's the x values that make y equal 0. So how can you tell which of these possible roots actually are a root? Plug them in, and you should get 0. If you plug them in and you get 0, then voila, you found your root. Okay? So, now the reason why this is kind of a pain in the butt, because there's a lot of work to it, because, you know, I had 8 numbers that I'd have to test. But it's a strategy and it works, so we're going to learn it. So how can you tell what the actual roots are? Since the roots are where y equals 0, we can just plug them in to see if they do in fact make the polynomial equal 0. Whichever ones do, those are the roots. So let's do an example here. Go ahead and write down example 2 here. Did I leave my pen on your desk? Thank you. All right, so here we go. Let's write the factors of the last term. Ready? So what are some numbers that go into 6, you guys? 2, 3, 1, and 6. And that's it, right? The next thing we're going to do is we're going to write the factors of the last term. I'm sorry, first term. My first term's coefficient is a 1. So what are my possible roots there? It's just 1, okay? That's pretty sweet when that happens because you don't get fractions this way. Because the next thing we're going to do is we make a list of our possible roots. And our possible roots are any of these numbers in the numerator over any of these numbers in the denominator. So it could be 1 over 1, 2 over 1, 3 over 1, or 6 over 1, which, of course, you can simplify all these, but for notes, you might want to write it like that, because sometimes you have to do that. It's 2, 3, and 6. So these are our possible roots. Furthermore, we don't know if they're going to be plus or minus, so we do need to check that. Now, in the extra credit videos, I'm going to share with you guys some really weird theorems that can actually rule some of those possibilities out if I get to make those extra credit lessons. I don't know if I'll get time to or not. We'll see. It's kind of a busy week for me. But there's some ways you can kind of rule some of those out, but those topics alone take like a whole day to explain, so I'm not going to get into them. We're just going to kind of keep it simple here. How can you tell which of these are the actual roots then? Plug them in and see which ones make the whole thing equal 0. So let's do that. Okay. Now, first of all, how many roots can this thing possibly have? It can only have 3 roots. Whatever that number is, that's the maximum number of possible roots it could have. So let's try 1 to begin with. I love to start with 1 because it's really easy. And this is why I gave you guys the calculators. So this one gives me 1 plus 4 plus 1 minus 6. Does that make 0? It does. Because these all make 6, and 6 take away 6 is 0. So we found a root. We have a winner. 1 is one of my roots. Let's keep going. Let's check -1 now. Oops, that's supposed to be a 4. So this makes -1, this makes 4, and this makes -1 minus 6. Does that make 0? Let's see. 3, Negative 7? No. So negative 1 is not a root. Okay, let's keep checking. And that's basically it. Okay? But I don't want to spend too long on this. You guys got the idea, right? You just plug them in until you get it. So I want you guys to do the same thing on this student practice. I want you to find out what your possible roots are, and then start plugging them in to see which ones actually are roots, and see if you guys can find some before the class is over. Okay? Yeah.